If you're asked to find all the zeros of the function, start with this, that the function has 4 zeros. Could be all 4 real, could be all 4 imaginary, or mixture of both, but the highest power dictates how many zeros we have. If you know you're not going to have a calculator available, you can always do it like this. Use the rational zeros theorem to think of all the nice, clean, easy zeros, which means you take the factors of the last number of 9, because that's the last number in our polynomial. So 1, 3, and 9 are all the different factors. And think about all the ways you can pair that up with the factors of the first number. Positive -1, positive -2. And so those factors are going to be, when you think about all the pairs, those are all the pairs. All the different ways you can combine the factors of the top and the factors in the bottom. So if you don't have a calculator, you got to plug in 1, 2, 3, 4, 5, 6. You got to plug in 12 different numbers and find out which ones are rational zeros. That would take a while. So if you do have a calculator, here's what you can do to save you a lot of those steps. Let's get a graph. Get a graph of this function. So I've zoomed in a version of the graph so we can look at the intercepts. Looks like it crosses at -3, which is one of the 3 numbers we thought we could have for a rational zero. And then we really just need 1 to start with, but it looks like -1 is also a possibility. +3 is also a possibility. So let's check that first one we found. We said it looks like it crosses at -3. If you plug in -3 in here carefully and simplify, you get 0. So -3 is indeed a 0. We'll start with that. We're going to take this polynomial and we're going to use the fact that -3 is a 0, and we're going to factor out an x plus 3 from it. Because if -3 is going to be 0, you should be able to factor out that linear factor, the x plus 3. We just need to find out what's going to go on in here. If you plug in -3 in here, -3 plus 3 gives you 0. 0 distributes and makes everything else be 0. So, okay, now that we know that -3 is going to be a root, let's find out what's left over. We'll use synthetic division. We'll put our root in a bracket. We'll copy down the coefficients of the thing we're trying to divide, which is the original polynomial. So I've got 2, 1, -19, -9, and 9. Then we carry down the first number. We multiply that by the root. Then you add. Then you multiply that by the root. And then you add. And keep going with that process. And you should not get a remainder. And we didn't. Indeed, we didn't. We got 0. So that's what all this stuff is over here. We found the quotient to be 2x to the third, subtract 5x squared, subtract 4x plus 3. That's what's going to go up here. So we've broken down the polynomial into a smaller bite-sized piece. Let's keep breaking it down. Let's go back to our graph. We said that -1 looks to be a root, and if you plug in -1 in there, you get out 0. So that means that we should have a piece that if we plug in -1 into it, it makes a 0. That's that piece I just added right there. So now we got to find out what mumbo jumbo is left over after we take out that piece. And again, well, I guess it's not again. I haven't said this yet, but you can just use the smaller factored piece. You don't have to go back and try to divide the whole one, because the whole point is we're trying to break this down into smaller bite-sized pieces, so we can find out all the roots. So do synthetic division, carry that down like we usually do. Same process as what I just did a second ago. And again, we don't get a remainder because x plus 1 is indeed a factor. So here's what's left over. You got 2x squared, subtract 7x plus 3. With synthetic division, the power should always be reducing by 1. So it's a little better. Here's what you could do to find out the remaining solutions. You could use the quadratic formula here if you want. You could factor this possibly too. But what I'm going to do is I'm going to go back and use the roots one last time. Positive 3 looks to be a root. So I'm going to factor this down into another smaller piece. I got x plus 3 still. I got x plus 1. And if positive 3 is going to be a root, then x minus 3 should be a factored piece, because I can plug in 3 in there and get out a 0. So let's find what's left over if I use synthetic division and take out an x minus 3 piece. Same process as before. We'll carry down that 2. We get 6. That makes -1, -3, 0. So here's what's left over. 2x minus 1. There we go. We've broken down the polynomial into 4 linear pieces: x plus 3, x plus 1, x minus 3, and 2x minus 1. Now we can find all those 4 solutions we were talking about. X equals negative 3 we saw from our graph. X equals negative 1. X equals 3. That's a terrible 3, but x equals 3. And then here we have x equals 1/2. And that seems to be seems to confirm what we saw in our graph. That looks to cross right about 1/2. Okay, so you might be wondering, why can't I just use the graph to begin with? You can always solve an equation by setting it equal to 0 and graphing, but sometimes you're not able to spot the solutions, and you can't see imaginary solutions otherwise. So you need to be able to know how to break it down into these linear factors. This is the only way to find out the imaginary solutions it's the only solution you probably have in your tool belt at this point. So knowing how to break it down into these pieces is important, so you can find those imaginary solutions. But those 4 are our answers.